For decades, the clinical expectation has been that after loading a two-piece implant, 1.5 millimeters of crestal bone loss is unavoidable. This loss matters because the crestal bone serves as the foundational support for the entire gingival architecture, maintaining the interdental papillae and soft tissue stability. However, researchers observed that intentionally mismatching the restorative components to create a physical step at the implant abutment junction can halt this expected resorption. In a traditional platform match design, the prosthetic abutment diameter is flush with the implant collar. Platform switching changes this geometry. A smaller diameter abutment is seated onto a larger diameter implant platform, creating an inward horizontal offset. This geometric shift challenges the long held assumption that a flush continuous margin between the implant and its restoration is the ideal configuration. Ensuring this bone level remains stable is a primary factor in long-term aesthetic and structural success of the implant. Before deconstructing the mechanics of this offset, we need to examine the peer-reviewed evidence validating its clinical performance. This flowchart highlights a systematic review process that narrowed hundreds of records down to 11 high quality studies to ensure the data is reliable. The results from this aggregated data indicate that platform switched implants maintain a 97.1% survival rate over a 10-year period. To see the specific millimeter level impact, we can look at a 3-year multi-center randomized control trial by Rocha and colleagues. They monitored 135 implants in the posterior mandible, comparing the flush platform matched abutments against platform switch designs using standardized radiographs. During the initial healing phase between the surgery and loading, bone remodeling was statistically similar for both groups. This graph plots the mean bone level change over 3 years. The platform matched group continues losing bone after loading, but the platform switched group stabilizes and shows bone regain. At 36 months, the data showed a significant preservation advantage of 0.39 millimeters, favoring platform switching. This evidence confirms that the technique works, but it forces us to ask how this geometric change alters biological and mechanical environment. To replicate these results predictably, we have to analyze the implant abutment junction across two highly distant domains, the biological and biomechanical. The biological vulnerability of all two-piece implants stems from the microgap, the microscopic space where the abutment meets the implant. Once the restoration is placed, this gap is inevitably colonized by bacteria. The body responds to this presence by forming a defensive ring of inflammatory cells around the gap. This cross section shows a traditional platform matched interface. The flush microgap sits on the outer edge, placing the inflammatory zone in direct contact with the crestal bone. The bone retreats from this inflammation, resorbing vertically to establish a safe biological width. Shrinking the abutment diameter pulls the microgap inward. The inflammatory zone moves towards the central axis, leaving a horizontal ring of exposed platform. This horizontal buffer isolates the crestal bone from the inflammatory cascade, preventing vertical resorption. Research suggests that even a small mismatch between zero point 0.3 and 0.45 millimeters is enough to provide the biological protection. While the histology explains how the soft tissue adapts, the implant system must still stand the repeated mechanical loads of mastication. Biologically, the platform switching manages the destructive vertical resorption through the creation of horizontal tissue buffer. The second pillar of bone preservation involves how the implant transmits occlusal loads. To clearly see how these powerful forces propagate deep into the surrounding bone structure, we use three-dimensional finite element analysis. A biomechanical study compared a standard platform matched implant to a switch design under a 100 Newton masticatory load. This map shows the load distribution for a platform matched implant. Notice the severe red and orange concentration is localized at the top outer corner of the cortical bone interface. These values represent von Mises stress, predicting where micro damage is most likely to occur. When the load is applied to the platform switch design, the severe stress concentrations migrate inward towards the center of the implant, leaving the outer bone in cooler, low stress colors. This reduces the maximum stress in the cortical bone by 36%. This study also tested an oblique load to simulate the lateral grinding forces of chewing. Under these lateral forces, platform switching provided an even greater stress reduction of 41% at the bone crest. Stress levels in the deeper spongy trabecular bone remained virtually unchanged. The geometric modification specifically protects the rigid cortical crest. While this redirects the stress into the internal abutment screw, the forces remain well within the titanium's structural yield limits. Mechanically, the platform switching redirects the stress to protect the crystal bone architecture from the occlusal overload. By combining these two pillars of data, it becomes clear that the platform switching acts as an active geometric intervention. This comparison shows how a single geometric shift addresses two different failure mechanisms at the same time. The exposed horizontal platform is both a physical stage for the biological width and a mechanical buffer zone for occlusal stress. While the healing phase is largely universal, the post-loading phase is dictated by the specific geometry of the abutment interface. The traditional flush designs often fail because they place maximum mechanical stress and inflammatory trigger at the exact same anatomical weak point. By moving the interface inward, the clinician effectively engineers a protective perimeter for the alveolar crest. Leveraging these synergistic biological and mechanical effects allows clinicians to move past the expectation of bone loss and ensure long term aesthetic and functional stability. Thank you.